Dear learners, in this session we will discuss about the concept which is associated with crystalline forms, and the concept is polymorphism. In 1820, a German chemist Ilhard Mitscherlich discovered differences in the crystalline forms of many elements and compounds. He observed that the two Greek words polus and morph, that is, the one having many shapes. So, the concept of polymorphism has been generated from the two words polus and morph. We have seen that a particular chemical compound with a distinguished molecular formula has a particular internal structure that has resemblance in the outer appearances. But in the case of some compounds, though they are having same molecular formula, but there is difference in their crystalline forms. For example, on your display, you are having a compound which is existing in three crystalline forms, but the base, the molecular formula is same for all of them. The compound is existing in monoclinic form, tetragonal form and cubic form. So, the capability of this compound to exist in different crystalline forms is nothing but your polymorphism. So, polymorphism is defined as ability of a respective compound to crystallize in two or more crystalline forms with different internal lattices. We have seen that the unit cell is the basic constituent of any crystalline form, and the arrangement of that unit cell in your crystal lattice or in your internal structure will have impact on its physicochemical properties. So when it comes about polymorphism, the polymorphism has impact on different arrangements in the unit cell of its crystal, and thereby it displays different physicochemical properties. So the physical chemical properties that alters along with polymorphism includes different packing properties. The change in the appearance of unit cell within your crystal will have impact on the packing property of that crystal. The bounding between two unit cell might be closed or they are slightly spread wide apart. So the different packing property is the output of polymorphism. At the same time, the properties like solubility, free energy and melting point, that are your thermodynamic properties, alters along with polymorphism. The position of unit cell or the position of atom within your unit cell will have impact on the spectroscopic property of that particular compound as well. And the properties like dissolution rate, stability and mechanical properties like hardness, compatibility and tabulating tensile strengths gets affected by means of polymorphism. So right from the arrangement or packing and the things associated with individual atom like your thermodynamic properties and spectroscopic property gets altered by means of polymorphism. At the same time, the polymorphism has impact on movement of particle and thereby allowing them to be strengthened or tightly or loosely held together in case of mechanical properties. If you are studying the polymorphism in elemental solids or in element, the capability of element to crystallize in more than one distinct crystalline form is known as allotropy. For example, if you are observing silver nitrate, the crystalline form of silver nitrate exists in rhombohedral form and orthorhombic form. But at the same time, if you are focusing on carbon, then the crystalline form of carbon may exhibit in cubic form and hexagonal form. The cubic form of carbon is considered as diamond, whereas hexagonal form is considered as graphite. So, if the polymorphism exists in your elemental solid or if element crystallizes in more than one distinct crystalline form, the polymorphism, the phenomenon of polymorphism in element is known as allotropy. There are several reasons of polymorphism, and it is essentially means that in different polymorphism the same molecule exists in different ways. Means polymorphism won't stands for alteration of your molecule. Polymorphism is the phenomenon associated with the same molecule existing in different forms, and the basic reasons associated with that unit cell and the atom located on the corner of each unit cell gives you the reason of polymorphism. The first reason is your packing arrangement. If you are observing atoms which are located on the corners of your unit cell, then the distinct distance between them gives you packing arrangement of that particular crystal. So if the difference in crystalline form is because of packing, then it is termed as packing polymorphism. In previous session of crystalline structure, we have seen that crystalline form has a different conformation. Means if you are dealing with molecule A, and the crystalline form of that molecule will have different conformation. If you are dealing with molecule B, molecule C, molecule D, likewise every molecule will have different conformation. But when it comes about differences in conformation of same molecule existing in different crystalline forms, please listen carefully that I am dealing with difference in conformation within same molecule. The point is true that every molecule will have different conformation, but when single molecule has different conformations, then this becomes a reason of polymorphism, and that is known as conformational polymorphism. In the same way, the term has been generated pseudo-polymorphism. In case of crystalline solids, we have seen one class, that is your solvates or hydrates, which means the engulfing of solvent or water molecule within your crystal lattice. But if the different crystal types are the result of process of hydration or solvation, if any crystal undergoes process of hydration and solvation, this hydration and solvation becomes a reason for polymorphism, and that is known as pseudo-polymorphism. This is more correctly referred to as solvomorphism. Means if polymorphism is due to solvation, then that pseudo-polymorphism is known as solvopolymorphism. Now, there are different types of polymorphs. Now, what is meant by polymorphs? Your polymorphs are the bases that has been generated by means of polymorphism. And this polymorphism can be classified into two types according to their stability. So, stability governs the base for the polymorphism with different range of temperature and pressure. And the polymorphism is categorized into two main types: monotropic systems and enantiotropic systems. Let's see what is meant by monotropic system and what is meant by enantiotropic system. If you are having one polymorph which is stable at all the temperature, means if you are having a molecule which is existing in different crystalline forms, so out of that forms, the one form is stable at all the temperature, but importantly below the melting point. Because if you are applying temperature above the melting point, there might be chances of degeneration or there might be chances of breakdown of your material. So you need to apply temperature below the melting point, and that one polymorph is remaining stable at all the temperature, and other polymorphic forms are being unstable. This kind of polymorphs are known as monotropic systems. Means out of the crystalline forms, one is stable at all the temperature, whereas other polymorphic forms are unstable. The next type is enantiotropic systems. If one of the polymorphic form is stable over a certain temperature range. Now remember, in case of monotropic system, that one polymorph is stable at all the temperatures. But in case of enantiotropic system, one polymorph is stable over a certain temperature range, while other polymorphic forms are stable over a different temperature range and pressure. In case of monotropic, we were observing that one is stable at all temperature and remaining are unstable. But in case of enantiotropic, one is stable at particular temperature and other polymorphic forms are stable over different temperature range, and that is known as enantiotropic systems. So basically, if stability is the concern for the types of polymorphs, then it becomes important to understand about stability of polymorphs. Out of the polymorphs, the form which free enthalpy is low at given temperature and pressure are considered thermodynamically stable. Means if you are saying that a particular form has a free enthalpy in the lower state, then you are referring that particular form as a thermodynamically stable, and other forms are said to be metastable state. So every polymorph is designated by a Roman number, and these Roman numbers are the order of their stability at room temperature, like form 1, form 2, form 3 likewise. Out of this one, form 1 usually has the highest melting point, whereas other forms are further categorized as unstable forms or metastable forms. So if you are plotting graph of change in temperature along with change in free enthalpy, then the monotropic system for the two different polymorphs, polymorph A and polymorph B, you will observe that they are behaving in the manner along with temperature. But in the case of enantiotropic systems, as you are changing temperature, a particular point will generate where both the polymorphs have differentiation in their stability. At particular point they are crossing one another, their stability is crossing one another, and that point is known as crossing point. In the case of unstable polymorphs, you can readily convert unstable form into stable form, but metastable forms slowly converts into stable form. So overall, when it comes about stability, then the free enthalpy is an important aspect to be considered. Overall case, the particular advantage of polymorph is that the chemical identity of material remains unchanged from one polymorph to another. So you can't need to distinguish between the chemical identity. The chemical identity will remain same though there is change in their crystalline form, so that a direct correlation between activity of that compound and solid state structure can be made. The relative stability and driving force for the polymorphic transformation, we are dealing with the constant temperature and constant pressure process. So at the constant temperature and constant pressure, the relative stability and driving force for that polymorphic transformation from stable to unstable, unstable to stable, metastable to stable, these are the transformations. So the polymorphic transformation from form 1, form 2 likewise is given by Gibbs free energy, and the internal energy available for chemical work is given in equation delta G is equal to delta H minus T delta S, where delta H signifies the change in enthalpy, delta S shows changes in entropy, and T is your atmospheric temperature. When you are solving this chemical equation and you are having negative value, this negative value assures the spontaneity of the polymorphic transition. So the polymorphic transition is spontaneous, gives you negative value, whereas positive value gives you that the process is non-spontaneous. There are different methods for the preparation of polymorph, and the methods are solvent evaporation method, slow cooling approach, solvent diffusion technique, vapor diffusion method, and vacuum sublimation approach. Let's see one by one. The first one is your solvent evaporation method. The solvent evaporation method is technically applicable for high melting substances. So that will give you material with high purity and higher yield. In this approach, the saturated solution of the drug is prepared in an appropriate solvent, and the highest quantity of solvent is removed by means of rotary evaporation, and all the process is continued with the air drying at various temperatures. So you can have different potential polymorphs once you are evaporating solvent, and you can use rota evaporators for the same. The disadvantage associated with this method is desirability of recrystallization. Means you can have the compounds that are need to be recrystallized. The second method is slow cooling approach. This slow cooling approach technique is frequently employed for the polymorphic forms which are of less soluble drugs in the solvent systems. but the solvent systems having boiling point ranging from 30 to 90 degree Celsius. And the reason for the selection of slow cooling approach is their ease and simplicity. If you are observing the slow cooling approach, then you can observe that the solute is heated in the solvent. So as to produce polymorph from this method, you need to heat the solvent and you need to add solute into it. The solute is heated in the solvent just above their boiling point to produce a saturated solution. And this solution is transferred to stopper tube which is connected to Dewar flask. This Dewar flask containing water at a temperature just below the boiling point of the solvent. Means you need to heat that temperature above, give the temperature above boiling point, and in the case of water, that is below boiling point. The Dewar flask is left in these conditions for several days. This technique may further be improved to obtain better crystal forms using different solvent mixtures. So you can have large scale of production and you can easily reproduce that material. But the disadvantage associated with this method is their yield value. This method gives a low yield with the chances of disordered and twinned crystals. The next method is your solvent diffusion technique. This method is employed when the amount of drug available for the process is in the low state and the drug is sensitive to air or your solvent. In this option, the solution is placed in a sample tube. Subsequently, less dense solvents is carefully dripped down the side of the tube. Means the less dense solvent is carefully dripped down the side of the tube using a pipette or syringe to form a discrete layer. The slow diffusion of the solvent results in the crystallization of API. At the same time, the process is quite tedious, which gives you low production yield. The next method is vapor diffusion method. This method is analogous to the previous one and is also applicable for the less quantity of the sample. In this method, the concentrated drug solution is placed as a drop hanging on the underside of microscope. The cover slip with the hanging drop is sealed with silicone oil over a solution which contains high concentration of precipitant. Due to higher precipitant concentration, the latter has lower vapor pressure than the drug solution. So the advantage is you will require a very less quantity of sample for crystallization. But the process is quite time consuming, which is expensive and gives low yield. The last method by which you can produce polymorphs is your vacuum sublimation method. Sublimation is known to offer excellent crystals of variety of compounds and especially in the case of air sensitive ones. This approach is frequently employed to induce crystallization with numerous variations of static and dynamic vacuum. So you can vary the static vacuum and dynamic vacuum which will have impact on the crystallization. So you can induce crystallization with varying the vacuum. A small amount of sample sealed under vacuum in a reactor is generally subjected to a temperature gradient in numerous manner, and the temperature of the order of 250 degrees Celsius can be easily applied along with the 10 to 2 millimeter Hg pressure. In this vacuum sublimation method, the crystal grows from the wall to the center of reactor and it gives the disordered or twinned appearance to the crystal. These are the methods by which you can produce polymorph. So here we have seen about polymorphism, that is the capability of compound to exist in different crystalline forms, and these variations at the low temperature and pressure based on the free energy has an impact on their stability, which is the best point for the classification of your polymorph. Thank you.